in the last lecture, I told you what is quantum Hall effect, and then I start by introducing Landau levels, which, as you will say, will really be the most important thing that for you to understand the quantum Hall effect. So then this lecture, I will still continue with the discussion of Landau levels. And just remind you that Landau levels is really just the solutions of particles, for example, electrons moving in the presence of magnetic field. And the electrons is moved in two-dimensional space, and the magnetic field is perpendicular to my my two-dimensional plane. So the Hamiltonian is really very simple. That it just can be written as the square of the mechanical momentum, that is my canonical momentum plus E times the gauge potential. And the gauge potential is gives me the magnetic field, which is perpendicular to my two-dimensional plane. And in the last lecture, what I did is that I choose the so-called Landau gauge. So which looks like that in one direction, in the x direction, the vector potential is just 0, and in y direction is x dependent, is x times b. Okay, and the point is this gauge actually preserves the momentum translation along the y direction, but it breaks the translation along the x direction. So a consequence is that the momentum along the y direction will be a good quantum number, which such that the wave functions will be the eigenstate of that momentum along the y direction. So then I choose you can easily find that this Hamiltonian tends to be a harmonic oscillator, which is really just px squared plus 2m and k squared. K is the momentum along the y directions plus x squared. So that's the harmonic oscillator, and sorry, it should be k, not k squared. So and that's the harmonic oscillator with your coordinates gets shifted, and the shift depends on the momentum. Okay, so then the solution of this harmonic oscillator will then be will have two labels. One, this n is just the label of which levels of the harmonic oscillator you are considering, right? And this and that's also what we call Landau levels, like with the nth Landau levels. And this k is just that momentum, right? So then the wave function will be like this. So I'm here, there will be some non-trivial normalization factor, which I will not specify because it's not important for this lecture. So it's, I get a wave exponential iky, which is really just tell me that the wave function is has a momentum k along y directions. Then I have this mid polynomials as well as an exponential factor. And here, this LB is the so-called magnetic length, which I will specify in a minute. And the eigenenergies of this Landau levels will be h bar times omega b. Omega b is so-called the cyclotron frequency, which I will also specify in a minute. So and you can say that the energies is independent of k, right? It only depends on n, which is like correspond to which Landau levels you are in. Okay, so there are two important quantities. One is this magnetic length, which is so it's called magnetic length. And the other quantity is omega b, that is EB over m, that is called cyclotron frequency. So in these lectures, you will, whenever you look at papers or different lectures or talks about quantum Hall effect, you will very often say those quantities appears. That's really the quantities that characterize the scales in the system, right? So yeah. And in this lecture, you will also say them appear again and again. So it will be good to have some idea about what are they. And later you will say there are actually some semi-classical interpretations about what are the physical meaning of those two quantities. Okay, so that's what I talked about regarding Landau levels in last lecture. And there were a few questions asking, yeah, so you may feel a little bit uncomfortable with this solution. One thing is that it seems my Hamiltonian, my original system, does not really break translation symmetry along x direction as well as y directions. But when I choose a gauge, I break the symmetry, the translation along x directions, and then in the end, my wave functions also breaks translations along x directions. So that feels a little bit uncomfortable. So you might be wondering whether that's an artifact of the gauge choice and whether I can have some smarter gauge choice such that I preserve all the symmetries. And the answer is actually no. And and it's also have very fun physics inside it. So let's think about just a process. Let's say I'm moving electrons. Let's say first I move it along x directions, right, with some distance that I call A1, and then I do it with in y directions, and then I move it back in the x directions, right, and eventually I close the loop, right? So let's say we just consider this process, right? And quantum mechanics tells us that actually for such process, you will gain a non-trivial phase that is called Aharonov-Bohm phase, right? Due to the Aharonov-Bohm effect, right? Due to the magnetic field that is perpendicular to my plane, right? So that means just consider this process. You will have so you will get a non-trivial phase factor, right? That depends on the charge of my electrons, that is minus E, and also the magnetic flux enclosed by the loop, right? That is what we learned in quantum mechanics. So what this formula is telling us is actually, it's just that my x and y is not commuting, right? They are not commuting, and what you have in the end is that you do have this. So if you permute those two, you get a non-trivial phase factor, just this guy, right? That is the consequence of magnetic field. So then, since they are not commuting, then the quantum mechanics principle tells us that you cannot simultaneously diagonalize those two translations. You have to break one. So that is a fundamental reason that you will end up with some sort of symmetry breaking in the end. But you should understand that the system does not really break the symmetry, and to really recover the symmetry is the fact that in the system I do so on each levels I do have degeneracies, and those degeneracies would help me to recover the symmetry, right? And it's so there's even a simpler example that that everyone familiar with, that if you just consider, let's say, quantum spins, right? We know, let's say, just spin 1/2 system that let's say you can write a quantum spin using the 3-component vector, and we know that those vectors are not commuting, right? Right, and that's very similar as the non-commuting relations of my tx and ty here. And then you know that you can write down this, but so then you know that you cannot find basis that is simultaneously eigenstate of all of them. You can only find a basis that is an eigenstate, let's say, of SC, but you can use the SZ eigenbases to superpose. You can superpose them, then you get the eigenbases of Sx, right? That's very similar in this Landau level story, right? Here, what we did is that we choose a gauge such that my wave functions have translation along a y direction, but it breaks the translation along x directions. Similar as the spin 1/2 case, I will end up with degenerate state, just like spin up and spin down. Then you are free to use those degenerate states to make another choice. You superpose them together, then you can get another basis that preserves that are the eigenstate of the other translations. So that's also, so that's basically how the degeneracy of the Landau levels comes from, right? That's really just a consequence of this non-commuting symmetries that comes due to the magnetic field. So, any questions? Yeah. It's the question was, what's the explicit form of translation operator? I think that should be let's say Tx should be this, right? I may miss the minus sign here. I never remember I should put a plus or minus there. Yeah, it's just from the canonical momentum you can define it, right? Yeah. Yeah. Question. Yeah. So the question was about whether the, yeah, it's a long question. I don't know how to summarize. Yeah. So it's about whether the system is bounded, and then so at the moment, I didn't specify what, I didn't try to put a bound on the system, and I'm going to do it in a minute. Only, yeah, only if you consider a bounded system, then the number of states will be finite, right? Yeah.
I think maybe another way. The question is, why is K continuous and N discrete? And,
So K is not continuous either. So yeah, the value of K depends on my geometry, depends on my boundary conditions, and so yeah. I will come back. I will talk about this in a minute. Yeah. The question was, yeah, whether Px, Py are commuting or not. The answer is no, right? It's come from this AB phase, right? So intuitively, it's really just that you have electron circle. You have an electron moving along this circle, then you pick up AB phase. That's how this non-commutation relation comes from. And usually we call this we call it as magnetic translation symmetry. Yeah. So, or maybe in fancy words, mathematical words, it's just this symmetry is realized projectively, not linearly. Yeah, that's the fancy way of putting it. So, all right. So, so now let's talk about that. Let's try to count the degeneracy of the system, right? So what we have learned from here is that this non-commuting translation really requires my system to have degeneracy. And then the important question is, what's the number of degeneracies? So let's talk about degeneracies. So now let's consider bounded system. Let's say I just have my system lives on a rectangular such that I have its width is Ly, its length is Lx. Right? That's the system I'm going to consider. And what I'm going to do next is that I'm imposing, since the gauge that I choose preserves the translation along the y directions, so then I'm imposing a periodic boundary conditions that is required. My wave functions will be invariant if it translates. If it translates along the y directions, it goes through the entire system. So that's the boundary condition that I'm going to impose. And then what we have is then just looking at the wave functions, you will learn that now my momentum will be quantized, right? And times that's 2 pi over Ly times an integer. So the momentum will be take discrete values. That's the typical case for a system with with periodic boundary conditions. Okay, so but we haven't but here it seems that the k can take any values, right? As long as it's 2 pi over Ly times the integer. And then the next constraint comes from that my system is also bounded in the x direction. And in particular, if you look at this wave function, what you can learn is that for each k, the wave functions in real space will be localized, right? At position, it will be localized at x around k times LB square, right? That's really because of this exponential factor, right?
You want to put a square here.
Oh, yeah, thanks. Yeah, that's a square. It will be localized at minus k times LB square, right? That's the wave function look like. So if you want to draw those wave functions, that's really that those wave functions will be just be extended in the y direction, but it will be localized in x directions. That's how the wave functions will look like. Of course, it has some structure along the x directions, but it will be mainly just localized as some stripe. Okay, and so we have two things, right? One is I have x. Let me just write equals to L k times LB square, right, for each wave functions, and I have I have my x to be bounded between 0 and Lx, right? So then that also gives me a bound for those momentum along the y directions, right? So then I can count the number of states. So for n in lambda level, right? I'm going to write LL as lambda levels. For n in lambda levels, remember that we are labeling lambda levels using this index n, right? And for n in lambda levels, the number of states is really that Lx over Lb square, and so that's the momentum, right? That's the bound for the momentum, right? Just from this relation, and over 2 pi or divided by 2 pi over Ly, right? That this comes from the fact that I require my momentum to be 2 pi over Ly times an integer, right? Then we end up with the degeneracy of the state. Right, that is the degeneracy of the state. Now you say you recover the democracy between x and y. Eventually the physical answers like degeneracies, and does not really depend on the gauge that initially would break the democracy between x and y very badly, but in the end you say that those physical quantities does not really depends on that. Okay, so and you also say that the physical meaning of this magnetic lens, that's roughly like the size of one electron would occupy, right? Right. This Lx times Ly is like the area of the system, and you can think each electrons is doing something like self-orbiting due to the magnetic field. That's a semi-classical picture, right? Classically, if you have electrons moving in a magnetic field, it will just do self-orbiting, right? And the radius of this orbit will be LB, and then the electron will occupy an area that is 2 pi times LB square, and then from this, you know how many electrons you can fit in one lambda levels. That's one physical meaning of this magnetic lens. Yeah, and also let me give you some idea about how large this degeneracy is, right? So let's say if we consider magnetic field that is 1 Tesla, and then this magnetic lens will be around, I think it will be around 2.5 times 10 to minus 8 meter, and the typical sample of the for people to realize the quantum Hall systems will have like Lx, Ly is 1 micrometer. So then you can find that then the degeneracies in each lambda levels, typically in an experimental system, will be around 10 to minus 10 to the ninth power. So that's a very huge numbers. So, and if you go to even larger magnetic field, you will get a larger degeneracy there. So, any questions so far? Yeah. So the question was, what's this degeneracy for, right? So that's a degeneracy of each lambda levels labeled by n, right? And the degenerate state is labeled by k. It's like you can have at each lambda level, you can have this capital N times of different choices of momentum, okay? Yeah. So any other question? Have a hole, you mean? You mean hole? What kind of hole are you mentioning? You mean geometrically the hole or the particle hole? Okay. Yeah, if you don't, let's say you have a lambda level and you don't fill the entire lambda levels, you can say, you can also alternatively view it as a case that you fill it with certain holes, right? Yeah, so let me also spend a few minutes continue with this semi-classical discussions, particularly regarding the degeneracy, which I think will be also useful for you to build some intuitions about quantum Hall physics. So I'm going to have, it's semi-classical picture.
Sorry, just a silly question. So the degeneracy,
yeah,
is an approximation, right? Because in Y it was exact, but in X you argued more or less based on this localization.
Yeah, that's a good question. So you can say quantum mechanically whether I can really have some wave function here, right? So yeah, it turns out to be an exact degeneracy. I mean, to really talk about the exact degeneracy, here what you can do is that you you also have a periodic boundary condition along the x directions, such that you have a torus. And there you can then compute the exact wave functions of lambda levels, because you need to take care of those boundary conditions and so on. And the solution for that will be some elliptic theta functions and so on. And then using that, you can compute the exact degeneracy, which turns out to be just this number. Yeah, that can be on torus. That's the exact degeneracy, and it can be computed exactly. Yeah. Okay, so I'm going to provide you some semi-classical picture. So yeah, I think whenever we really study quantum physics, it's always good to develop some semi-classical pictures which can guide you through to the answer. Okay, so semi-classically, what we can do is that's just think about the equation of motion, right, of the system. That is just classical electrodynamics. So that's my, so I do have this classical equation of motion, right? And then we can find a solution to be xt, x it will be time dependent, and I have some capital X and minus r times sine omega bt plus phi, right? And here you say the appearance of this cyclotron gap, that's really correspond to the frequency of this self-orbiting semi-classically. Okay, and this x and phi, capital X and phi, are really, and also r will be, depends on your initial conditions, like where the electron was, and also what's the initial velocities of the electrons. So similarly, we can also have y will be cosine omega bt plus phi, right? And this capital X and y is really just the center of my orbit of electrons, right? And you can of course rewrite your x and y as I'm just using those two relations. You can rewrite x, and we know y dot will be my canonical momentum, right, along y directions, right? Similarly, for this capital Y, we can get it equals to and then what you would find is that you can compute the commutations between capital X and capital Y, right? Remember, so here I rewrite it as the combination of coordinates and mechanical momentum, then they have some commutation relations. Remember that I also make use of such commutation relations to define the original Hamiltonian for Landau levels as some harmonic oscillators and so on, right? And that's very similar here, yeah. Probably no. Okay, yeah, you're probably right. Yeah, it's probably a denominator. Yeah, thanks. Yeah, so you can compute the commutators, and I will not do the algebra for you, but in the end, you will find that this x, y is not commuting. So in some sense, that's so that's actually related to the so-called non-commutative geometry, that you just don't really have your coordinates commuting, right? So and then we learned that from quantum mechanics, that just due to the Heisenberg uncertainty principle, that I cannot really specify the position. I mean, there will be some uncertainties for about where the electrons is really as, right? So then roughly, then that means so then you can intuitively view that my electrons will occupy a finite space, which is order of LB square, right? That just due to the uncertainty principles. So then that means that means that for each electrons, so then pictorially, what you can have is really that each of my electrons will occupy this LB squares area. They are not overlapping with each other, and eventually they occupy the entire space. That's also, so then from this you can roughly get a number, the number of degeneracy, right, is Lx times Ly over Lb squared, right? Of course, you miss the factor 2 pi, but if you think this this semi-classical picture even harder, then you can even recover this 2 pi factor. So yeah, and that's a semi-classical picture I want to talk about. So any questions? Which phase? Yeah, they are the same, right? Omega b times t. Yeah, the phi are the same, right? Yeah, both of them are phi, right? Sorry.
Why are they the same was the question. The question was whether we could have phi x and phi y, if that would still be a solution.
Yeah, so just looking at this, right, you would tell that the phase should be the same, right? Okay, so there's another important quantity that I think I didn't mention. Let me also write it there. It's also will appear a lot in this lecture, as well as in discussions of quantum Hall physics. That is called, that I denoted as phi 0. That is the so-called flux quanta. So how should I write it? Let me see. It's 2 pi times h bar over E, right? And it's called flux quantum, right? It's the minimal unit for the magnetic flux you can have, right? And here, then alternatively, I mean, using this magnetic flux quanta, alternatively, you can also write the degeneracy as like E times B times Lx times Ly. No, we don't need E. B times Lx times Ly over phi 0, right? There's also another intuitive way to view this degeneracy, to counter the degeneracy. This, in my nominator, that's really just a total flux that I have in the system. And in the denominator, I have this phi 0. That's the minimal flux in my system, right? Then the degeneracy is really just counts how many flux quanta do I have in the system. Each flux quanta corresponds to 1 electron, right? That's the, yeah. So yeah, and I think it would be good for you to really be familiar with those three different quantities. They're very important in a lot of discussions involving quantum Hall effect. Okay, questions? Yeah. Depends on what? Yeah, that's why the question was why the flux quantum doesn't depend on B, right? It doesn't depend on B. That's why it's a fundamental quantity, right? And yeah, it's really characterized what's the minimal flux you could have in the system, right? That's also the flux of a magnetic monopole you can have. Yeah. It's like the minimal unit of monopole, right? Of course, we know we haven't found it yet, but yeah, it's like the charge of monopole, just like the electric charge of the, yeah. All right, so in the rest time of this lecture, so I think, so far what I did is to solve Landau levels, right, in terms of this symmetric gauge, right? In terms of this Landau gauge, right? And in the end, I end up with wave functions that have momentum along y directions, but localized in the x directions, right? Although I explained that you don't really break the translation along the x directions because you have massive degeneracies. You can use them to, you can superpose them together to get a state that preserves translation along ly direction, lx directions, right? So, but still, this geometry doesn't, this answer doesn't look quite symmetric. So so in the rest of this lecture, I will also, I will tell you another choice of gauge, which end up with different types of bases for Landau levels, and which is also very useful in the later discussions. So, and the gauge is called symmetric gauge. So the vector potential I will have will be minus y times b over 2, and the y component will be x times b over 2, right? And for this gauge, the thing is you can say it breaks both translation along x and y directions, but the good thing is that it actually preserves the rotation symmetries. And so then you can kind of imagine that, so here in the end, my Landau levels can be so if you consider that, so my Landau levels will be pictorially look like I really have circles, right? Each orbitals in my Landau levels will be can have some well-defined angular momentum that circling around in the system, right? Pretty much similar as the picture that I have here, right? So let's try to, so with this gauge, then let's try to solve the, again, solve this Landau level problem, right? So you might remember that, I introduced in the last lecture, I introduced this so first, let me still write down the Hamiltonian for my system, right? I have this, it's the square of the mechanical momentum, and the mechanical momentum is P plus E times A, right? And then in the last lecture, I introduced creation and annihilation operator that I can rewrite the Hamiltonian as A dagger A plus 1/2, right? And this A is pi x minus I pi y over 2 square root of 2h bar E times B, right? I define these creation and annihilation operators, and then the energies of its Landau levels is really just the same as the energy of the harmonic oscillators, right? And this is so through this you can easily get the energies of each Landau levels, but you don't know the degeneracy. So you don't quite say the degeneracy there. So and in this symmetric gauge, actually we can kind of say this degenerate state. What you can do is that now you introduce another operator that I called pi prime, which just reverse the sign of my mechanical momentum, right? And now you say different from mechanical momentum, this guy will be gauge dependent, right? And you can compute its commutation relations, which I will not do for you, but you can do it as an exercise. So like pi x prime and pi y prime are not commuting, and they are also my pi x is not commuting with pi x prime, which will be proportional to partial ax over x, and my pi y is also have this with the commutation between pi y and pi y prime will be proportional to partial ay over partial y. Okay, and the last commutation that I have is if I consider pi x and commutator between pi x and pi y prime, which will be same as commutator between pi x and pi y and pi x prime, which will be proportional to partial ax over partial y plus partial ay over partial x. Right. That's, yeah, you can do this in the exercise. So, and then so here the relation is general for any gauge. And now you can say, I do get a good, yeah, but now you say the good thing comes out for this symmetric gauge, that is all those commutators become 0, right? That means now I do have pi I commuting with pi j prime, no matter what I choose for this I and j, right? That means now I do find then I can use those pi prime. I can similarly define creation and annihilation operators. Which is very similar to this A, and I call it as B. Right. Yeah. Here, for some reason, I invert the sign here, but it's really a convention. So now what you can have is that you can label the states on each lambda levels with two labels, right? One is n, which tells you which lambda levels you are, right? That also, eventually the energy depends on this n, right? And this m comes from this new variable that operator that I introduced. And then the state will really just be, I create n state with creation operator a dagger and create m particles with the creation operator b dagger, right? Starting from vacuum, right? And the energies of each state will only depend on n is independent with m, right? So now you say in this symmetric gauge, I can also get degeneracies. I can kind of capture the degree of freedom of those degeneracies on each lambda levels in a purely this algebraic manner. So you can also work out the wave functions of under this symmetric gauge, right? As I explained, pictorially, what you really have is very similar as the case for the Landau gauge, right? Each wave function on each lambda level, right? The wave functions will be localized on a circle, right? And it has well-defined angular momentum, right? And the radius of that circle will depends on the angular momentum. So let me write down the solution here. So it would be more convenient to introduce a complex variable that I called z, and z bar, which will be I define z as x minus iy. It's slightly different. It's different from what you usually do in complex analysis. Z bar as I plus iy, right? So then you can write this derivative of z as 1/2 partial x plus I partial y and partial z bar. Let me write here. Partial z bar will be so then with some algebra, which I don't have time to go through, but you should do it in your exercise. That is, I can find that the operator A that I defined will now becomes minus I times root 2 LB plus J over 4 minus LB. And my B operator will be minus I square root 2 LB partial over this. Yeah, let me write it, please. Yeah. So I should say that I'm using partial as is partial z, and partial bar is partial z bar. And LB will be that's how you can write down the operators, right? So now if we look at the lowest Landau levels, right, that correspond to n equal to 0, so such state will be annihilated, right, by A, right? So, and then what you can immediately you can get is that the wave functions for the lowest Landau levels, right? I'm gonna call LLL, just refers to lowest Landau levels, will be of this form. Right. Again, I get an exponential factor similar to the case of this Landau gauge, and Fz is a holomorphic function of Z, right? You can show this, for lowest Landau level that n equals 0, the wave function should have this form, right? And then to get other state, and then you also, with the form of this operator B, what you will end up with is the wave functions. Let's say for 0 m will be proportional to, so then you know the specific form for this holomorphic functions is Z over LB m square times minus Z square times this exponentially decaying factor. That's the wave function that you have. You say that with in this Landau gauge and for the lowest Landau level, the wave functions really becomes a very simple form, right? It's really just Z to the power m times this exponential factor. And you can also show that each state will have angular momentum m times h bar. So and for example, should I write? Let me write it here. So you can define an angular momentum operator that is I times h bar x that's my angular momentum operator, and you can rewrite it as the this Z and Z bar I introduced. So it will have this form, right? Then you can show that those state has well-defined angular momentum, right? If I ax this h at my wave functions, I will end up with m times h bar and phi. Right? That tells me that the picture that we conjectured at the beginning, right? Since my vector potential preserves the angular momentum in the end, I should get wave functions that has a good quantum number and of angular momentum. And you can further look at this wave function, right? Then you know that the wave functions will be localized at a position depends on m, right? Because besides this exponential factor, I also get Z to the power m, right? Then you can look at the function to ask what does the wave function look like. And we'll find that so the wave function will be localized at some circle with a radius r equals 2 pi m times LB. Right. that's how the wave function looks like, right? For m equal to 0, that's really just, right here. Right. There may be some extra number like 2m plus 1 maybe. I'm not entirely sure about this. So, but the picture is really that now in this symmetric gauge, right, I will have the wave functions just be the localized as circles, right? And the radius of the circle will depend on the momentum of angular momentum of that state. And this picture is also very important later in the next 2 lectures, probably next lectures when I talk about disorders and so on, then you will see this picture come again. Okay, I think it's a good time to stop. So.
Okay, very good. We have time for questions. Let me just ask one because it's very naive. Why didn't we go to radial coordinates for this gauge? These coordinates, z, z bar, and all this. Wouldn't it be simpler to just write Hamiltonian in r and theta, or is it naive?
Because I think it's simpler in this form because then I can, then the wave functions will be really just holomorphic functions, right, of this. Yeah. I don't know how, for the case of r and theta. And I don't have time to talk about this in this lecture, I guess, but this form turns out to be extremely useful in the fractional quantum Hall. So you will say that the famous Laughlin wave functions is really just written using those z and z bars, which will become very simple in this formula.
This might be naive, but could you repeat, please, what the notation bar n, m angle means explicitly?
Sorry, I missed you want me to explain what
Could you repeat what the notation bar n, m angle means?
Oh, you mean this thing?
Yes, what is it explicitly?
Okay, so that's the label that it labels the states on my lambda levels, right? The first number n just refers to the which lambda levels we have, right? So remember, so it's the energy of the state will depend on n, right? And m refers to the degenerate correspond to. So in this picture, this m correspond to the angular momentum of the state, right? So remember, on each lambda level, each lambda level is highly degenerate, right? And then in this case, I can label different degenerate states using their angular momentum m, right? Does this answer your question? And operational-wise, those states can really just be created by a dagger and m dagger, right? Defined as here and here.
So, I had a question. Here, the angular momentum is in the z direction, right?
It's angular momentum.
So what about the x and y direction? Because in this case, will depend on the z position, right?
It's a two-dimensional space, right? You only have angular momentum. So the rotation axis should be perpendicular to your 2D plane, right?
Sorry.
Hello. Before my question, I'm going to say some ideas to get to the question. Okay. In the last class, you showed us that we choose a gauge invariance to form a semi-classical approach because it was how do you say? But useful. And now we are trying to. Well, now we are trying to use the gauge symmetry to make a physical representation to the pseudo momentum operator. My question is, why? Well, my question comes from this. I'm thinking that using polar coordinates is easier, but we are trying to use the pseudo momentum operator to get to quantize the level of degeneracy. That's my question. I don't think it's clear. My question.
Could you repeat
Yeah.
the last sentence? Yeah.
Forget it. I'm going to write it so I get the right idea.
Maybe the question is, how could one come up with the idea of using this P prime, right? It looks a bit.
Yeah.
Why did you come up with P prime? Is this the question?
Yeah. Why?
I saw it in the lecture notes. It's not I come up with this. So, I don't have. Yeah, to be honest, I don't have any intuition, like where this comes from. Sorry.
Well, maybe it's just similar when you're trying to find the eigenstates of the angular momentum. Just it's the same algebra, like when you have x minus iy, and you have like dx plus iy and dx minus iy. That's the same thing as like jx plus ijy and jx minus ijy, which is j plus and j minus, and you just like raise and lower the angular momentum. So it's basically the creation and annihilation, the A and the B. It's similar. I think that's why it's useful to use this set of coordinates, because the algebra is very similar to quantizing the angular momentum operator.
Yeah, I think you're probably right. Yeah, good. Yeah. Thanks.
More questions? You can.
Hi, I didn't get it like quite right, but when you get the wave function for the lowest Landau level, you solve a differential equation with the application of the A operator.
Yeah.
Okay, so the question also goes to, is analogous if you apply the B operator to like an n, 0 state? Or, I mean, it is the same?
It's not. Yeah, the thing is, for A, it's partial over of the Z bar, right? It doesn't act on here. Right?
Okay.
Right. So then it's really just this part is a solution of this, right? Okay. But for B, this partial acts on FZ, right? Then it's different.
Okay.
Right.
Yeah. Okay, thanks.
So this angular momentum is specific for this gauge, right? Because we construct the pi. So we can interpret this as the angular momentum
or is just some dependence, some value dependent on the gauge?
So after if we choose this symmetric gauge, then the system is rotation invariant, right? The Hamiltonian is rotation invariant. Then the solution of my Hamiltonian will have this good quantum number angular momentum.
Okay, but something
it comes from the gauge, but the thing is, yeah, because the system has a symmetry, so we are allowed to do so.
Okay. Okay. Thank you.
More questions? Well, we are right on time, so then let's thank Yin-Che again. And we'll have coffee break now and return